before, we're going to be using trig substitution again, but we have a bit of a twist on this one. So our integral is 1 over x to the 4th times the square root of 9 minus x squared dx. And you can see from the square root here, this looks like a trig integral part. Now, we also have it multiplied by x to the 4th. Let's try not to worry about that till after we do the trig substitution. So our trig substitution here, we want x to be either sine or cosine. It really doesn't matter because you're doing 1 minus sine squared or 1 minus cosine squared. It will work out either way. But since there's a 9 here, we want our coefficient to be 3. So let's just say 3 sine theta. So our derivative substitution, dx equals 3 cosine theta d theta. So let's do all our substitutions and see what happens. So what we get is, instead of x to the 4th, we get 3 sine theta to the 4th. We get square root of 9 minus x squared, 9 minus 3 sine theta squared. And instead of dx, we have 3 cosine theta d theta. So let's do a bunch of simplification and see what happens. Now, on the bottom, under the square root, we're going to get 9 minus 9 sine squared. Remember that you always end up factoring that out. And we'll be left with 1 minus sine squared, which is cosine squared. The square root of that is cosine. So this whole thing in parentheses, or that entire radical part, becomes 3 cosine theta. And that's exactly what we have right there. So this is all going to cancel out. So remember that, again, this becomes 3 cosine theta because we're going to factor out the 9 of the radical, and it's going to become a 3. We have 1 minus sine squared, which is cosine squared. Square root of that is cosine. So that all cancels out. And what we're left with is 1 over 3 sine theta all to the 4th. So 3 to the 4th is 81. So I'm going to put that 1 over 81 in front of the integral. And what we're left with is 1 over sine to the 4th of theta d theta. So that integral is one in which we're going to need to do a couple of different things here. What we're going to do is treat it as cosecant to the 4th theta d theta. And we're going to use our rules to determine what we need to do here. So cosecant to the 4th, remember that rules for cosecant and cotangent are extremely similar to the rules of secant and tangent. You just might have negative signs that you need to be aware of. So we want to keep cosecant squared theta and think about what the other rule, or the other term is going to be. Cosecant squared is going to be equal to 1 plus cotangent squared. We get a 1 over 81 here. So what we can do here is just do a standard substitution, because the derivative of cotangent is negative cosecant squared. With substitution it will cancel, we'll just get stuck with the negative sign. So what we're going to do is say u equals cotangent theta. That means that du is equal to negative cosecant squared theta d theta. So when we plug in our substitutions, what we're going to get is negative 1 over 81, because I'll just put the negative sign in front. The cosecant squareds are going to cancel out, and we're just going to get 1 plus u squared du, because our u was the cotangent theta. Well, this is a pretty simple integral now. So we have negative 1 over 81 times, the antiderivatives here are just u and u cubed over 3. So what we need to do now is do our substitutions back. We're going to have to do it in 2 stages. First, we need to say that u is cotangent. So we have negative 1 over 81 cotan theta plus cotan cubed theta over 3. Keep in mind, too, that this one can be done using... You could have done this at the beginning by calling this cosine theta, because 1 minus cosine squared is still sine squared. That works out either way. And this would have ended up in secants and tangents instead. But the answer ends up being the same. So u was cotangent theta, we plugged that back in. Now here's our answer in terms of theta, and now we need to do our last thing, which is our trig substitution. So let's draw the triangle for what we have. Angle theta. This tells us right here that sine theta is x over 3. So remember that sine opposite over hypotenuse, so we have x and 3, which means this is square root of 9 minus x squared. Remember, it always ends up being the part you had in your integral. So we're set up with our triangle. Now we can get all of those things that we need. Cotangent is going to be opposite of tangent. Tangent would be opposite over adjacent. So cotangent is going to be adjacent over opposite. So we have root 9 minus x squared over x. Over x. Excuse me. But actually, before I do that, we had a cotangent in each term, so I can factor that out. So I can factor out one of the root 9 minus x squared over x terms. What I'm going to be left with is 1 plus cotangent squared over 3. So what I'm going to get here is root 9 minus x squared over x squared over 3. So all I did here was take out one of the cotangents. Cotangent was that, like we had just showed on the triangle. And then I get 1 plus cotangent squared over 3, plug that in also. So this simplifies down to negative root 9 minus x squared over 81x if you combine these things. Excuse me. And then on the inside, we're going to have a couple of different things here. We're going to get 1 plus, so this is going to give us 9 minus x squared over 3x squared, being fully factored out there. Let's see what else we could do. So this is, since it's 9 minus x squared over a single term, we can split that into 2 fractions, and the reason we might want to do that is that the x squareds will cancel out in the second term. So we're going to get 1 plus 9 over 3x squared minus x squared over 3x squared. Those cancel out, so we can simplify this a little bit further to be 1 minus 1/3, and we get 9 over 3x squared to cancel. So this is all just algebra from here, but what we end up with is we're going to get 3 over x squared from canceling out the 9 over 3x squared, and we're going to get 1 minus 1/3, which is plus 2/3, which then you could combine to one fraction if you wanted to, or you could have done that from the beginning. There's a variety of different ways to do this here, plus c, of course. So even when a function seems to have an x term or something that you think might throw off the trig substitution, normally it's still going to work. So as soon as you see that square root and the perfect setup for a trig substitution, everything else is just going to be a matter of figuring out the integral in some other way. So in this case, you can see a trig substitution turned into one of our trig integral forms. And then we just had to go backwards 2 steps to get our integral in terms of x. So that's a really common type of test problem also.